Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Antonio Condorelli with us today. Hello,
Hi
Antonio.
everyone. Hi.
Antonio, where are you located at?
Now I'm currently at the EGC Lab, which is a laboratory which is in the suburb of Paris, so 22 kilometers southwest of respect to the city of Paris. And yes, here I'm doing my first postdoc
Ah,
in the framework on the peer-to-peer collaboration, let's say.
very
So
cool.
it's
And that is a very awesome shirt. That is a great shirt. I love it. I love it. That is fantastic. It's very appropriate too, considering what we're going to be talking
yes.
about today.
This morning when I choose my outfit, I say let's make something that talk about science.
You dress for the occasion. That's
Exactly.
wonderful. And Antonio, we're coming up on December. Does it snow in Paris?
No, I have to say that the last 2 days, like, it started to be like a kind of like cold, but not so cold.
Okay.
The last week was a little bit tough, but since now so far, like, no snow at all. I have to say I'm in Paris since 2 years and something, and I never seen like the snow here. So so far, like, it's cold, but we can resist it.
Very good. Very good. Cool. And Antonio, what do you like to do for research?
So so I say I did basically through my small career within the Perugia collaboration. So I started my master I did in the Netherlands. My PhD I did in Gran Sasso Science Institute, which is a research institute that is in Italy.
Yep.
And now I'm in Paris. I'm I'm a very bizarre, say, type of scientist belonging to the UG because I'm not an experimentalist, but I'm not a theoretical either. I'm what is called a phenomenologist. So what I'm
Yep.
trying to do exactly is try like to make these two words, so different words, try to combine. So as you might see today, for example, for this paper that we are going to talk about, try to take what comes out from the experiments of data and try to provide some to say something about astrophysical implications. So like try to make them talk with astrophysical models, and this is it. Sometimes it's complicated because, of course, two different words, two different approaches, but I think like it's worth like at a certain point like to make them combine.
Beautiful. Cool.
So
That
I'm very Italian. You might see from my hand, from my
good. Oh,
face.
good. Hands are good. Hands are good. They make great poster images. And that is going to bring us to this very awesome APJ article.
Yes.
It is open access. It's the open access era. People, you can go grab a copy for free. Go get one. Impact of galaxy clusters on the propagation of ultra-high energy cosmic rays. And Antonio, take us away.
Yes. So yeah. So I was as I was saying before, like this is exactly like one of the example of this work that we are reading, I don't know, over the last days and of the last say weeks. No, say this work is published since November, so we worked it. We're a little bit before about that. So the idea is to try to understand how an object like that, such a big object with a very huge magnetic field, very magnetized, with a good density of interstellar medium, could impact with to ultra-energy cosmic rays propagation. So we don't know yet, despite the effort of the peer-to-peer collaboration and the TA experiment, we don't know yet which are the source of ultra-energy cosmic rays. What we can do is that we can try to imagine that some source can accelerate particles, and then, but in order to connect what we see at Earth with what we imagine, what we want to do is to try to make the link between the two. And this link is exactly computation of the propagation of ultra-energy cosmic rays. We know that the universe is not empty, and so wherever the ultra-energy cosmic rays are produced, during the path they lose energy, they lose mass,
Sure.
because they interact with the photon field that we have in the universe, either the cosmic microwave background and the extragalactic background light.
Right.
So in this case, what we want to study is what happened inside galaxy cluster. So in the first part of this introduction, what I just say is that I introduced the problem of ultra-energy cosmic rays, which are the sources, and once they are produced, which is the role of the environment inside the source, which role plays.
Yeah.
Here, a small introduction of or what are galaxy clusters. Galaxy clusters are basically the largest structure that we see in our universe with a very, very huge mass. You see here, like in the pointer 10 to the 14, 10 to the 15 solar masses, very huge magnetic field, order of few microgauss.
Yes.
And basically, I want to combine these two words like together in a certain way. So
Cool.
here, like if we go down here, say that okay, here we're talking at a certain point about the upper limits on flux of neutrinos and gamma rays that in a certain way confirm what we see from ultra-energy cosmic rays. So
yes,
that ultra-energy cosmic rays are nuclei and not protons, as was believed, I don't know, 20 years ago, or something like that.
yes.
And these protons has to be produced somewhere. There was also some paper that here, like I cite, where they say that also galaxy cluster could be responsible for their acceleration.
Okay.
This is not what I'm gonna describe in this paper. What I'm gonna describe in this paper is the impact of the environment. So assuming that we have a source inside the cluster, what the cluster does to these ultra-energy cosmic rays.
Okay.
And okay, so here in the last part of introduction, I just say that there are different works that was done before, and not all of them agree, literature, let's say. So I believe that this paper is timely because try like to provide how to say a new approach like to solve this problem. So what is the impact of this environment on the accelerator?
I'm with you.
And so this I hope will be enough to what concern introduction. And so I can already say that the paper is structured in this way, since we want to know what is since the title says what is the impact of this environment. In section 2 that we're gonna dive in very, very soon, we're gonna model the galaxy cluster. So how a galaxy cluster is made. Then once we know how to describe the environment, we're going to pass to the propagation. So propagation inside the environment.
Yes.
And then the last two sections are we basically talk about the results. So what comes out from our simulation and what this mean in terms of astronomy, like in general. And on this, we're going to talk about say possible implication and future development of this work.
Nice.
Okay, so start with the galaxy cluster. We are very, very lucky because normally each object in a certain way like has his own properties. No, if you take an astrophysical environment, for example, a vast galaxy, an AGN, each one has his own magnetic field, gas density, and whatever. This is also the case for the cluster, but for the cluster we are very lucky because at least for nearby cluster we say that they are self-similar object. What does it mean?
Okay.
It means that if we take their pressure profile, they have more or less exactly. So this equation number 1. It is possible to parameterize the pressure profile for using a single formula, basically. So using a single behavior, which depends only on this F of M that you see in the formula in the formula 1, which depends only on the mass, this M500, and on Z. So this means that if I give you, oh, perfect, there. So if I give you the mass and the redshift of a cluster, you are able to retrieve what is the pressure profile. So how much the pressure will change as a function of the distance from the center.
Cool.
And this is very important because in this way we can basically use a catalog when the only information that we need are mass and Z.
Yes.
I want to comment on this 500 because someone can say, why don't you call it M? Why don't you call it 500?
Yeah. Okay.
The point is that the quantity that matters to describe the environment is not the total mass, but it's called the M500, which is the mass at a distance from the center, which is called the R500. R500 is the distance at which the critical density of the cluster inside. So like is the distance at which you reach a critical density, which is 500 times the critical density of the universe at that given redshift. So
Gotcha.
if
Gotcha.
you take if you take a cluster of a given redshift, you know that at the distance at which at the center you have a 500 times the pressure, the critical density is this R500. And so this is the crucial quantity to parameterize everything. So if you go to figure 1, for example,
Take a look at figure 1. These are protons.
exactly.
Wow.
So this dashed vertical line that you see here around 1 megaparsec. This is exactly R500. So we believe that our assumptions are valid from, let's say, 0 to R500. This is basically the range in which we want to explore it.
Okay.
So,
right.
okay, so for me, so the plot that that we are seeing now is not pressure because it's not we're not going to see the pressure profile, but you might see that in the y-axis I wrote thermal proton density. Why this? Because in terms of propagation of ultra-energy cosmic rays, we don't care about the pressure, but the pressure can be used to retrieve two important quantities that are important to consider diffusion of particles inside this environment.
Yes.
The first one is indeed the density of target. So what we want to know is how much target, how much material you find as a function of distance, because of course, the more an object is dense, the more likely this particle could interact, could lose energy, lose mass. And so these are quantities very important to us. And a second quantity that we're going to see later is the magnetic field profile. So how much the magnetic field will change as a function of distance. So here you see, here is just to show you how our model, so this self-similar assumption that we made, talk with respect to the few experimental data that we have. So in the blue line, you see a measurement of what is the density for coma. For example, this is one of the most famous cluster for coma cluster. And with the different color, we found different assumption. So for example, that one used in the paper is the red one. It's called UPP, that means universal pressure profile. So what I was saying before.
Equation 1.
Yes, and then we have also the assumption. If we can come back to the question, please, I can show you what does this.
Sure.
Thank you very much. So if you go down, exactly. So for example, this UPD that you see, for example, in equation 2, is another assumption where they basically try to try to parameterize also the thermal density as a universal function by Pratt and others. And this one is shown in green in the figure 1.
Gotcha.
Yes. What instead do we use it is it's green and yellow. These are two different universal density profile by two different authors. What we're using instead is the red, which means that we are taking pressure from equation 1, and then do what we do like in pressure in equation 3. So basically saying that pressure and density in this environment are correlated. In particular, one is the power law of the other, and this is called the polytropic relation. So this is the way in which we retrieve the density of target. You see here we can retrieve you see how many electrons, protons, even helium target we can retrieve, and this is basically the way in which this this was done.
I'm with
A
you.
very similar approach is performed using considering the magnetic field. If we can, if you want, we can start seeing figure 2, which is the following one.
Profile, okay, portion of
Yes,
the pressure.
I'm gonna come back. And this,
Okay.
okay, so here you see like the same. So once again, from the universal pressure profile,
Yes.
we can have some. I mean, we can, starting from some assumption, we can have a hint of what is the magnetic field strength, and then compare to the experimental data. So the same exercise that was done before. This, in this case, still the blue line is a paper by Bonafede et al. And in this case, we are considering two different assumptions. One is called, which is this one, okay, which is basically the red and the yellow line is called the equipartition. So we
Yes.
assume that the energy goes at the same times to what to say, thermal and magnetic field.
Yes.
In this case, we have to assume something from the beta, also from the velocity of the plasma, according
Yes.
according from different work.
Okay.
And there's also the possibility to relate directly the magnetic field to the density profile. So, for example, in green here we show what happens if we take the university density profile that was shown in green in the previous plot, and from there, using a parameterization that we see maybe in one of the equations that we are seeing before, and directly compare it to the magnetic field. And here you see basically this plot will show you basically which is the uncertainties that we have in this in our modelization, let's say like that.
Okay.
So
Cool.
if we come back very fast on the equation, just to
Yep.
comment what I just said exactly. So equation 4 is what I was saying before about equipartition, and instead the other way, assuming that the magnetic field is frozen into the plasma, this adiabatic assumption. Normally, this is equation number 5, where you see that a direct operation between the magnetic field strength and the density in the environment. I just want to say that this plot that I show you now are made using coma cluster, which is that one that we know better in terms of measurement. But the appendix on this paper, you find a figure set, which is a super cool thing that only a PJ can allow, in which you can basically see the same plots with different type of cluster that we test.
Perseus, for example, yes.
Exactly. For example, Perseus, Hydra, and all other clusters.
Okay.
So I think that I don't know if I have to add something else. Okay, so I think that the two in a certain way well describe the part of modeling. So to us, we start with an idea and we come back basically with this, as I say, magnetic field profile and gas density profile.
Yes.
What does it mean? It means that for each point inside the cluster, inside the environment, I can tell you what is the target, what is the density target in each point of that, and how strong is the magnetic field in each part of that. So we have all the ingredients to perform a propagation of particle inside that. So
cool.
What we do now, what we do in the next session is consider what happened to a ultra-energy cosmic ray, so to a particle like that is propagating in this environment. So what is the possibility that this particle interact with something, or what is the possibility that this particle diffuse, so start like to run away. So in order to do so, we use a Monte Carlo code, which is called a SimProp, which is a Monte Carlo propagation code well known in the ultra-energy cosmic rays community. I am one of the developer like that. We normally use it to consider only the extragalactic propagation. So when this particle propagate through the universe. And this one, of course, is much easier because through the universe you don't have target, you don't have dust. In this case, I made some change to making uses in a source environment. So in a certain way, to take into account also, as what we said, that here we have magnetic field and we have a certain
Number density.
exactly a certain number of density. So let's consider what can happen like to a particle. Let's say it can interact through interaction with photons, and here you see what we have in equation 6. So when you have an interaction with photons, in this environment we are considering photons of CNB and DBL that I discussed in introduction.
Energy.
So
Okay.
so in this case, the number of interaction divided by time depends basically of this double integral, which take into account the cross section. So because the photon nucleus like in the interaction, and from the photon field. So for this n gamma. This is a very well-known formula that tells us basically which is the interaction time for photons. Together with this, we have an interaction with also protons, as I said, and this is in a certain way a new entry for what concern ultra-energy cosmic rays propagation. This was done by interfacing SimProp with an hadronic interaction model. So an hadronic interaction model is normally is what is used in our field to take into account, for example, how ultra-energy cosmic rays interact. We know that these particles, I mean, we never measure directly a proton at 10 to the 20 or an atom.
No, we see cascades.
Exactly. And so how the cascade is developed, this is normally modeled using hadronic interaction model that have some input of hadronic physics and basically and basically tell us how many pions or secondaries, whatever, are produced. So here, instead of taking into account the interaction in air, as we say for shower, I use it to take into account interaction in the environment, so in this case, in the cluster.
Cool.
So what happens is that when we have an hadronic interaction, SimProp directly call Sibyl 2.3D. Sibyl 2.3D come back to SimProp, we say, you produce this number of secondaries, this number of photons, neutrinos, whatever, and in a certain way it takes into account this interaction.
Yeah. Okay.
Particle can also diffuse because I mean they are not obliged to interact all the time, and this part I basically said the way in which we consider diffusion in this place. So this is a very standard. Consider a Kolmogorov shape for what concerns low energy. Then a drop at the highest energy, considering the fact that when the Larmos radius is higher than the coherence length, we are in a quasi-linear system. This is Subedi 2017 that we are mentioning here. Yes. And then, of course, when you have a diffusion time which is smaller than R over C, you just go ballistic because particles cannot go at a speed higher than. And so all of this, all this time scale are summarized in figure 3, if you want.
Let's go. Ooh, link scale. Okay.
So here, like the game here on the left side is the shorter wins basically. So the process they have the shorter length is the one that is most likely that happens. So if we, for example, we take protons at 10 to the 18, you might see, so protons are red, but okay, for diffusion, which is the same for the two, we take black. So you might see that diffusion for proton at 10 to the 18 is much lower. So diffusion for proton is the black line. So you see here is much shorter with respect to interaction with photons, which is the dot dash line, and protons, which is the dash line. So it's much shorter. This means that at 10 to the 18, protons will likely escape with respect to interact. So it means that escape. Instead, if we go, for example, at 10 to the 20 something, 10 to the 20.5, something like that, you might see that the interaction, which is this dashed green line, dot dash line, and diffusion, which is instead this solid black line,
Yes.
are in a certain way same order of magnitude. So this means that, for example, for nuclei, we expect the highest energy that these two processes can compete in a certain way. So in particular, can either interact or diffuse. Okay, so this is just to explain how this our model works. Okay, so we come back like to read here. Like, let's see, like if because I think that we have to discuss
Okay.
some assumption. So can you zoom out? So I can
Sorry.
see, like, no worries. What is it? So in this say implementation of propagation in the intercluster medium. So here we're discussing what are all the assumptions. So of course we have to consider a certain EBL model, a certain photodisintegration cross-section model. Here is the way in which we include the magnetic field, because in a certain way, the magnetic field is included in that way that you see it here. And so in a certain way, we compute the effective length that a particle travel through inside the cluster. So in absence of magnetic field, say how a particle diffuse, we know. But we also know that in the presence of a magnetic field, this causes a delay because particles start to spiral. And so in a certain way, we can compute which is the effective time, so the effective length, and then, of course, in a certain way, the effective time, because all these particles at this energy moves at the speed of light. And so what we said is that if I have a particle propagate in my Monte Carlo, and it takes a times to escape from this environment, which is higher than the time of the universe, we stop this particle and we say that this particle is trapped, so it does not escape. So it can keep interact, but always has such a low energy that we don't care, because what we want is we
won't see it.
Exactly. And so, okay, so here, like at the very bottom of the page, I start describing the methodology. Say the propagation is divided into a given number of steps. So I imagine that inside the cluster there's a source somewhere starting shooting ultra-energy cosmic rays.
Okay.
And so I imagine like to separate the position of the source with respect to the escape with a certain given step. And at each step, I ask myself, this particle interact or escape? If this particle interacts, of course, all the daughter that are produced are then self-like propagated. And yes, so okay, so here is I just summarize like what I say. So I choose an injection point. As I say that the length scales depend on the position, because of course, if I'm in the center, if I'm in the border, change the magnetic field, change the field, and whatever. So if a particle reach the border, it's considered that escape, so it's propagated through the extragalactic space. If instead, as I say, remains trapped, is not propagated anymore, it's considered that we will never supposed to see that particle there.
Right. Let me ask one question. When you inject the particles, what energy do you give your nitrogen whatever?
Yes, so in this case, we are assuming that we inject in a range which is 10 to the 17 to 10 to the 21 electron volt. But our goal, you might see later, will be try to describe ultra-energy cosmic rays which are above the angle. So the angle is a feature that you have in the ultra-energy cosmic ray spectrum, which is a few times 10 to the 18 electron volt. So we're interested in the highest energy part of the ultra-energy cosmic ray spectrum.
Oh, here it is. I answered my own question. Here we go. We inject 10 to the 4 at this energy. Okay, thank you. I led that pretty good. Okay.
Yes. So here, for example, I show two plots where I see what happens. So figure 5. Yes. So figure 5, for example,
let's
show
do figure 5 first.
Yes, show what happened to the escaping flux if I consider say bigger and bigger cluster. So Bigger cluster means a higher magnetic field. So what you might see, so on the y-axis, you see basically the ratio between what escape and what I inject. So you see that for a very weak environment, so for example, the red line, which is 150 nanogauss, you see basically that you have always one. So it means that everything that you inject escape because the environment is not dense enough to make some change. And then you see that time I increase my magnetic field, you see that at low energy we have something that moves like step by step. Why? Because these are basically low energy particles that they interact, and so in a certain way they move. So here exactly I put the ankle energy because what we're interested in is to try to describe the right hand side part in a certain way. This is the part that we want to parameterize. Okay, so this was just like an exercise I like to show you. Now I think yes. So can you say?
So on at the very highest B, it's basically 0 all the way to the end, and then we get this enormous jump around 10 to 20.
Yes. Okay. So this is not physical. So it's just a matter of representation. The reason is the following: since here what we're showing is the ratio of two quantities. So what happened here for the very big because here what I was saying is written here, yes. Is written the spectra are normalized to that expected without interaction. So it means we are normalizing an escaping spectra with what we expect with no interaction. So what happens is that this one is always 0, 0, 0, 0, 0, but arrive at a certain point in which even the denominator is 0 because we basically are at the end of the spectrum that we inject in a certain way. No, because you remember I said that we inject between 10 to the 17 and 10 to the 21 something. And so what happened is 0 to 0 causes like this bump.
Gotcha.
So of course, like this one, I mean, we do not take it as I say. We can say that for very high magnetic field, basically. We do not expect nothing to escape.
Okay, cool.
You can say it.
Thank you.
And no worry, you're very welcome. And then if I remember well, no. If before talking about this figure 6, I don't know if there was something before. No. Okay. So here just this will give me the opportunity to talk about what we want to do. So we are very ambitious, and so what we want to do, we want to provide a parameterization. So this one that you see in Formula 9, 8, and 9, 10, 11.
Yes.
That describe how is the transparency of the cluster.
Yes.
For each cluster. So it means that you give me the mass of your cluster, the redshift, and the position of where is your accelerator, like inside the cluster, and what inject, of course, because it can inject, as I say, proton. I can inject also iron. I can inject whatever. And me, I can give you basically from a single formula, which is the transparency. So how much this environment allow ultra-energy cosmic rays to escape, and how much instead, like in a certain way, is opaque for this way. And so this is basically was the effort coming from our simulation. And now we can come back with the figure 6, which I think is the most important plots of my work. So exactly. So where we found actually like what is physically interesting. So the points that you see here with different colors are simulation coming from my work.
Yes.
The lines are the parameterization. So the lines are just to say that we believe that above the angle. So again, say the white part, we can describe what escape.
Angle here.
What is interesting to see is that it is true that for protons, even if we put a very high magnetic field, you still expect to have something that that slightly escape at the
Yes.
base very narrow. This is not the case for heavy nuclei, for example, for helium and nitrogen, and then we can go up to silicon and iron and whatever. And the reason of this is the fact that while proton, if they interact, they still remain protons.
Sure.
This is not the case for a nitrogen. So a nitrogen, once interact, is not nitrogen anymore. Like, can produce a pile of secondary, whatever, like, depends on
It
interaction.
breaks. Okay. Yes, yes, yes.
And so what we found out here is that since Auger at the highest energy did not measure protons but measure nitrogen or
Okay.
like intermediate heavy nuclei,
Mhm.
what we believe is that these environments are very opaque to ultra-energy nuclei propagation at the highest energy.
Mhm.
And this effect, we believe, that has to be taken into account once we go and search for plausible ultra-energy cosmic ray sources. And this is, I think, the most important things.
That's a beautiful figure. Beautiful figure.
Yes. So now we can, okay, so this one we can comment it. And so now we can start like to talk about what does that mean. So if we
Okay.
go a little bit down, okay, so this is now just mathematical details to how this is explained. So section 4.2 told us basically it's an investigation on the systematic, basically say like, what is the, because of course we made several assumptions like to arrive to this point, and also someone can say, yeah, but what happens if you change these details of these details? And so in this section, I try like to summarize this. So how this depends, for example, on the diffusion coefficient that we take. We found that there's more or less a factor of 2. Assumption of the magnetic field and gas density profile. You see like the curve that I showed before in figure 1, figure 2.
Yes.
We believe that this is yes, order of a few percent, so very small with respect to the uncertainties that we have. What is the impact on the hadronic interaction model? Yes, so here, for example, here I discuss also what happens if you consider also interaction with the star contribution, because here we consider
Ooh.
photons only
Yeah.
from DMB and DBL. And so we believe that basically everything within a factor of 2, our results does not depend on all these assumptions that still are main assumption.
And
Okay.
so the quantitative impact of these assumptions, this is measured by the error bars in figure 6. Is that
So
what these error bars?
no, so these one are only statistical uncertainties.
Got it. Okay.
But then we provide like we try like to see what happened, for example, for example, for the transparency function for protons, what happened if we consider a different a different pressure profile, or we consider a different
Yes.
target.
Got it.
And we see basically that and we
That's
can change for a few percent, but the key message, so ultra-energy cosmic rays are are likely to not escape from galaxy cluster as ultra-energy cosmic ray, ultra-energy nuclei. This remains does not depend on any of these assumptions.
Okay. Cool. Thank you.
And then we arrive at the very last section to have this discussion in which you say what is the impact of this work. So in the first part, I just summarize what I just talked about with you. Then here we say basically that this work. Yes, of course. Like this is we try to start our work to say that we use a very detailed description of the environment and whatever. Important point that we are discussing is that this one this result is valid in a galaxy cluster. If you have filaments or sheet where the magnetic field is lower, you can still easily have an accelerator that produces ultra-energy cosmic rays, and you might see it. Yes, so we arrive at the point that you just highlighted. So we believe that this work would have a strong impact on ultra-energy cosmic rays astronomy, because of course, even if ultra-energy cosmic rays are charged particles, we are doing anisotropy studies. So
Mhm.
basically we measure the energy cosmic rays coming, and we try to point towards the source. And so if you have a galaxy cluster which is opaque, this should in a certain way coming into say into your model. So expecting that this is that from one point you should not expect to have ultra-energy cosmic ray sources.
Okay.
And this one we hope to apply this
Okay.
to our arrival direction analysis. And okay, that's it. There's to say like a possible application of this work in a future paper we are writing, but maybe this one we can discuss it later. And okay, and so this is basically yes. So okay, so here I'm saying that yes. So here we discuss three different hotspot, for example, three different classes, which is Coma, Perseus, and Virgo. In particular, Perseus and Virgo are very important for what I was saying, ultra-energy cosmic rays
Yeah.
studies. And
Yeah.
exactly, so this in a certain way take into account this effect, we see that tend to in a certain way improve the modeling of the sky map that we have. So make in a certain way this work that we're seeing here. Exactly. So tend to make the model and experiment closer in a
Cool.
certain. And yes, also here, okay, so here I try to be critical to myself in the very last part. So like, what we possible like we miss in this case. So one crucial question could be the secondaries, because I say before that a nitrogen once interact is not
Right.
nitrogen anymore, but
Right.
it's
Totally.
also not true that like what remains disappear. No, so nitrogen becomes protons, becomes helium, and so how these interact, how these secondary flux influence your results.
Mhm.
My point is that I check basically what is the flux of secondary, and these are still a factor of 2, something like that.
Okay.
They are say they can be very important for interaction below the ankle, but above the ankle at
Yes.
the highest energies, they do not consider like they do not change the result. So still belong with this within percent that I was talking before, like to say
Right. Okay.
that's not the way interact. And then yes, okay, and then okay, I'm talking about here future development. And this is very interesting. The idea is that CTA, Cherenkov telescope array, see an excess from Coma cluster, and
Yes.
so in principle, if you have the tools to do the propagation inside, you can have in a certain way a link between the gamma rays that you see
Ah,
and the ultra-energy cosmic rays propagation. So you can use the excess of gamma rays to constrain what is the maximum energy inside the class. So this is a very cool thing. This my
yes.
personal taste.
Cool.
And this is it. In the appendix, as I was saying before, like there's a now you see like a plot on Perseus, but here
Perseus.
with all the cluster that I show you before, like this one,
Uh-huh.
this exercise was done basically for in which we put experimental data, models, and see
Uh,
basically that we are more or less always be able like to describe what is the behavior of the gas density profile and magnetic density profile. And I would say that this is say more or less this is the most important things that I want to say about my paper. So modeling, methodology, and then astrophysical implication of our work.
awesome. Awesome. Antonio, thank you so much for walking us through your very lovely article. Fantastic. And you touched on it a little bit there toward the end, so I'll just push on it a little bit. Where do you think we go with this over, let's say, the next couple of years? You mentioned you've got something in the books right now, but is there additional data that will be coming from Auger or one of the other detectors? Is there additional theoretical work that could be done? How do we deal with secondaries, etc.? So just sort of next steps. Where do you think we go with this over the
Yeah.
next couple of years?
So we believe that this work could be okay. So from an experimental point of view, so we try to distinguish experimental and modeling efforts.
Yes.
Experimental point of view, Auger just finished some upgrade. So the upgrade, in principle, will probably shed us some lights on what are. So we expect to have much more data, which much more precision. And the
Okay.
idea, if you're able to measure together arrival direction, energy, and mass, you can have also an estimation of what is the deflection, and you can much more
Yes.
easily point towards the source. From a modeling point of view, we have another paper that we want to submit next week, still on APJ, where we where we apply this method on in our to our model. So we basically believe that the source of ultra-energy cosmic rays are transient source, so
Sure.
events that happens one in a while, and we might see that take into account this galaxy cluster filtering and basically tuning a little bit, like see basically how often they have to burst. We are able to describe energy spectrum, mass composition, and arrival direction of ultra-energy cosmic rays. So I believe that this work can be used for many other works take into account ultra-energy cosmic rays astronomy, and and I hope that in certain way would help us our effort, like to find the sources of ultra-energy cosmic rays.
Cool. Well, I really look forward to seeing that paper next week. And in general, I really look forward to seeing this topic advance over the next couple of years, particularly with new instrumentation and all that going on in
Yes.
OHA and other instruments. So it'll be very cool. Be very nice. Nice.
Thank you.
That will do, everyone. Thank you, Antonio. And
Thanks to everybody. Hope you enjoyed.
and I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.